My name is Anton Kukumar. I'm the calibration lead for the NIRCam team. But I'm giving this presentation on behalf of the entire team. Basically, everybody in this team has contributed in one way or another to the various calibration programs that we do. Presenting basically the current calibration status for our instruments. And in this case, it will be the description of the calibration observations, our current modes, and how we're calibrating them, and more or less the calibration accuracies for each of the different modes. Just to give you all a very quick overview of NIRCam, it has two redundant sides. We refer to them as modules A and B. The figure here shows one side, then there's basically an optical bench, and there's a mirror image of this on the other side. Each module, so in this case, one of the modules we're looking at here, there are basically two cameras to it. There's a short wavelength and a long wavelength camera. They would be these gray square boxes. The blue one is a short, and the red one for the red beam is a long wavelength. The short wavelength consists of 4 detectors on each module. They're each 2K MIRCAD detectors with a pixel scale of about 0.03 arc seconds. The long wavelength camera is basically twice the pixel scale, so 0.06 per second, and it only has one MIRCAD again, one of these per module. There's a dichroic, which is more or less in the middle of the assembly here, so that splits the light. So simultaneously, you get a field of view that covers both in both the short and the long wavelength. And there are pupil and filter wheels containing a total of about 48 optical elements. And I've given the references here, and also there's a link to the NIRCam page for more details. So just to show you what this looks like on the sky, as I say, so this now shows both modules looking at the sky, and the red outline here would be for the long wavelength channel, and so you can see there's one SCA seeing the sky in each module, and the 4 blue outlines show you the 4 blue chips on the short wavelength channel in each case. So, and there's a gap of about a few arc seconds between the short wavelength module SCAs, and there's a larger gap, about 40 arc seconds between the two modules. So there are basically a few different modes. I'm showing you here just the subarrays. So you can image the sky, of course, with the full detector, or you can break it up into subarrays. Imaging has a few different subarrays. Most of the imaging ones are on the B module. There's some in the corner here of B1 they use for point sources, unresolved, very compact sources. And there's some larger subarrays in the center of the B module. Those are used to image maybe planets and so forth. The use of subarrays is that they give you faster readout time. So you can, if you have very bright sources where you want to do time series, you can use subarrays. Chronography, there's a separate set of apertures and masks and subarrays up top, and they go onto the A module. And then also we have GRISM time series. There's a bunch of sub-GRISM subarrays down there, mostly on the A module. And we have those in both long and short wavelength. I'll talk more about those in due course. The optical elements, as I mentioned, each module has 48 of them. There's 2 filter wheels, and so there's both one filter wheel and one pupil wheel for the short and the long wavelength channel. Each filter wheel has 12 filters for each of the short and long wavelengths. And then the pupil wheel has some additional filters that couldn't fit onto the filter wheel. Plus, it has some additional optical elements. It's got the GRISMs, it's got dark, basically a blank, it's got a dispersed Hartmann center, it's got Leo optical elements for chronography, and it also has weak lensing and some other elements for pupil wheel and alignment, wavefront sensing. And I'll talk more about those in due course. So basically, in summary, NIRCam has 5 observing modes. We can do imaging, chronography, time series, GRISM, and GRISM time series, and then also wide field slitless spectroscopy. GRISM time series basically does sort of a single object mode. And our calibration plan really then addresses each of these different modes in turn. And I'm just listing here really for your reference. I won't read them all out, but each of the different subarrays, different modes use different subarrays, and also different, some of them are only on one or the other module. So here's a summary of our complete calibration program. This covers all the cycles. This is basically post-commissioning. These are the program IDs. You can find these. They're all public. You can find them on the JWST program webpage, the same place that you go to look for your geo programs. And for this presentation, I'll be going basically through the different modes. So on the left-hand column, it breaks out for you at a very high level, we've got detector level, things like dark current, persistence, linearity. We've got imaging, all the different kinds of imaging calibration that we do. Then we've got the cross-instrument and also just general flux calibration. Then we've got chronography and spectroscopy. So our calibration program basically covers each of these modes. So I'll just describe for you today basically at a high level what our calibration involves. So we start off at the detector level, the dark current, read noise biases. The summary here is that we monitor the full frame and the subarrays. You get darks throughout the cycle, basically twice a year, cycling through all the subarrays and the full frame. And then monthly, more frequently, going only through full frame, but you can cut out pieces of that for the subarrays. And that's mostly to get bad pixels. The darks have a bunch of different properties and uses. You can characterize, of course, the dark current, or you can also use them to characterize 1/f noise, intrapixel capacitance, IPC, crosstalk, bad pixels, and also super bias for all the sine subarrays that we use. I'll note here that the short wavelength detectors have very low dark currents. So right now we do not yet have nearly enough signal to noise in the dark to actually make a pixel by pixel dark current for the short wavelength. It's much too low. But the data is still useful for constructing bad pixel masks for the short wavelength. The long wavelengths have high dark rate, and so for those we actually have pixel by pixel darks, which we apply in the pipeline. The darks are also useful for amplifier glow. So especially for the subarrays, they've got much shorter frame times, and so the amp glow accumulates, and so you can that can have significant structure across the subarrays, and so the darks are used for that. And so this is just to give you a couple of examples here. And also, I'll mention on most of these slides, I'll mention the names of the team members in NIRCam who are typically leading these analysis efforts. Some have transferred out of the team at this point, but the analysis basically is led by different subgroups of the team. So this is just to show you visually what a couple of the darks look like. The one on the left here is in the short wavelength, one of the module B short wavelength detectors for NIRCam, showing you the full subarray, but it's quite low signal to noise, basically a signal to noise of a couple per pixel. And you can see there are various features in the detector that show up in the darks. The one on the right is for the long wavelength B module, and so that has high signal to noise, and so we can apply these in the pipeline and subtract them out to get a dark current subtraction. And as we continue accumulating darks through future cycles, we'll build up signal to noise, and eventually I think we'll end up being able to make pixel by pixel marks for the short wavelength detectors as well. But the overall use is monitoring and also bad pixels. Here's just a little schematic of our monitoring for NIRCam. This basically goes from more or less from the end of commissioning, the bias level on, and again, just showing an example here for one of the B module SCAs, showing that the biases are basically stable. So we track these pretty regularly and we report them to the project. This also shows you the read noise, again, on one of the amps for, I think this is for NIRC-B1 amplifier number 1. And so if there are ever any changes, these are the first line of defense for monitoring changes that we might come across, and then we would adjust our calibrations accordingly. Another aspect of our detector level calibration is persistence. And so here we have an initial set of persistence that was given to us by the ground test, but there's some indication that on orbit the behavior is somewhat different. So we have persistence calibration programs to basically characterize this in more detail. Cycle 1 and 3, we looked at star clusters, specifically Omega Cent. In cycle 4, we've changed this to a more diffuse target where we looked at Jupiter, putting that on all the SCAs. And in cycle 5, we're fully covering the SCAs with M31, which we blur with the weak lens and the grism to smear it out. So the basic goal here is to saturate significantly the detectors by factors of about 100 in terms of the full well depth. And then you have several hours of darks after that to track how the persistence decays. And so the persistence is very different from one detector to the next. Here just shows you a few examples. On the NIRCam A module detector 3, you can see the time, the persistence decays quite slowly, more than a couple of hours after the end of stimulus. There's still quite a significant trend of persistence with time. compared to the NIRCam long wavelength module, there the persistence decay is much faster. And so graphically, there's a web page where you can go to that shows you all the details about our persistence, and this figure comes from that web page. But this just shows you how the persistence is quite different, both among different detectors within a module and also even across the different modules. The long wavelength modules are quite well behaved in terms of persistence, but the short wavelength modules, some of them are better than others. If observers have a target that only needs to fit on one short wavelength module, we would typically recommend using, for example, a fairly clean detector like the SCA B1 on the B module. That tends to be quite well behaved for persistence and also has good behavior in terms of other properties. Another aspect of our detector level calibration is linearity. And so this is a similar kind of observation, but different. Cycles 1 to 3, we looked at stellar fields, in this case, the LMC astrometric field in 47 tuc. The complication there is that if you look at stars, there's an electronics effect called the brighter, fatter effect. It relates to how incoming photons are represented on the pixels on the detector. And the more charge you accumulate, the more they spread out. And so, in fact, the detector physically shrinks in terms of its charge. And so this kind of complicates the analysis a bit for linearity. A positive side to that is that we can actually use those data to characterize the BFE in more detail. But if you want to decouple brighter fatter from actual nonlinearity, the best thing to do is to then complement these programs with diffuse sources. So in cycle 4, we looked at Uranus. We don't want to saturate quite as much as we do with the persistence. So Uranus is a bit fainter. So we looked at that in cycle 4, and in cycle 5, we look at M31, basically using the weak lensing to blur out features for that, for the linearity. So this just shows you some of our current results. Generally, the detectors are pretty linear. There's the graph here shows you the normalized deviation from linearity. So once you fit a linear slope up the ramp and you take out the linear component, this shows you the residual. So overall, we're within a couple of percent of linear, maybe up to about 2 or 3% of average 2.5. There is an interesting knee at a fluence of about 40,000. So before you hit the saturation of 65,000, and currently we're analyzing the data just to try and characterize this just a bit better. Once we get our full data set with the extended sources, we'll be able to characterize the full linearity behavior, and then we'll incorporate that into the pipeline. So turning now to our imaging mode. So for imaging, there are basically a few different aspects to it. So the first of these is flat fields, and I'll discuss a couple of different ways in which we're getting these. Sky flats is our dominant input to the flat fields. And so most of our sky flats actually are constructed from archival geoscience data. The sky is high enough in basically all the filters, most of them, that we can construct very good signal-to-noise sky flats just based on archival data. So we don't need external calibration observations for most of the flat fields, nor do we need internal lamp flats or anything like that. We can do it all directly from geo data. And there are just a couple of filters for which we actually do need external data, which don't have enough coverage. They're not very well used. And so currently, for our current cycle, the filters we're focusing on here are F140M on the short wavelength and F250M paired with that on the long wavelength. And you can see these in the plot. The plot here is represented in terms of uncertainty. So the higher you are in the plot, the more uncertainty there is, the less signal to noise. So it's basically inverse signal to noise. So most of the black points on this plot, these are wideband filters, and you can see most of them, the uncertainty is about 2% or less. In other words, the signal to noise of these would be better than 1 or 2%. But there are a few filters which are more than 1%. So F140M is sitting at about 2.5% error. And same thing on the long wavelength. The 250M is the highest of the medium bands on the short wavelength, on the long wavelength. So we have a parallel observation with NIRCam. So NIRCam, it turned out, also had a need for sky flats, and so NIRCam basically takes advantage of that. So we're building up sky flats for these additional filters. These are useful not only for skyflats, they're also useful for our WISP templates, and also just in general for improving our accuracy of our flats. So a couple of additional calibration details for these. We have seasonal variation of skyflats, mostly due to Zodi. And so you see here an example in the 356 backgrounds. There's a trend there. It's about an amplitude of 4%, which we can calibrate out. And our overall accuracy for flats is about 1% overall. Again, most of the filters on that previous block. I'll show you here also the WISP templates. We've recently delivered September last year version 3, which has much better signal to noise for removing the wisps. That's a scattered light feature in NIRCam. I'll show you at the end a set of links to our pages for resources for scattered light. And so these skyflats are useful for creating WISP templates that you can then subtract from your data. There's also an additional way of getting at flat fields. That's called L-flats, or long, sort of low frequency. We've just started creating these L-flats based on stellar observations. So these are completely complementary to making skyflats based on background observations. L-flats actually involve observing star fields, measuring photometry, and then creating flat fields based on that photometry, much the same as what's done on HST. And so we started analyzing these. We expected these would improve our skyflats based on sort of external diffuse observations. Preliminary analysis shows some of these improvements. So the color bars here typically have an amplitude of about plus or minus 2% or so. So you can see there are low order residuals across these detectors based on both the skyflats and the stellar fields. So once these are removed, we expect that these will greatly improve our flat fields, especially in the corners where there's often a deficiency of data. So stay tuned. Once we incorporate these L-flats, we expect all our flat fields to be substantially improved. Coming now to photometry, we've got a number of programs which deal with imaging photometry. And so one of these deals with the transfer of flux or calibration of flux from our subarrays to our full frame arrays. Turns out that you need to do different calibrations. Subarrays have different electronics readout settings for amplifier and gain and so forth. And therefore, the flux calibration is slightly different in a subarray compared to full frame. So these programs account for that calibration. The bottom line here is that the count rate accuracy for our full to subarray transfers are basically good to within a couple of percent for most of our subarrays. And so these calibrations are aimed at just ensuring that calibration is as good as possible and continuing to calibrate flux for subarrays that don't have quite as much data. This shows the accuracy for 3 different modes: imaging, GRISM, and coronography, left, middle, and right, respectively. And again, most of these are within a couple of percent. You see on the x-axis here shows you different subarrays, and there's sort of a couple of percent of offset which are being calibrated with these modes. And as we continue in the current cycle to get more data on these subarrays, we continue to improve these offsets. But overall, the bottom line is the agreement is within a couple of percent for basically all the subarrays. Then there's also relative flux calibration across the detectors. And this is a different effect completely. This is between all 10 detectors on both modules. Our previous accuracy for the past few cycles post-commissioning was about 3 or 4%. I'll point out our requirements actually, project level, were about 5% for the mission. So we're well within that, but we would prefer to improve our calibration as well as we can. So we were reaching 3 to 4% for our initial first couple of cycles. Currently, we're now at 1 to 2%, but you really want to do better than that. So here's an example of science impact. This is one of the, I think, 47 tuck from one of the papers. Martha Boyer is busy writing this up. Again, analysis by Arun Barrage and Ben Sundquist on the team as well. And the left-hand plot here just shows you, it's a bit hard to see on this plot, but there's definitely an offset in the color magnitude diagrams of about a 0.01 magnitude horizontally. The left panel being before this correction. The right-hand panel is after applying this relative flux calibration across all detectors. And The idea is that the histograms on the bottom now line up to after having removed about a 1% photometric difference across the SCAs. We're seeing this in other programs too. I'm involved in some science programs for extragalactic science, where also you see of order 1% flux differences between modules for galaxy fluxes, let's say. And so this kind of calibration program will remove that. So here's how we're designing it. The basic approach is to observe 47 tuck in this case, to observe basically a large-scale mosaic to move the modules A and B onto the same piece of sky. So here we'll be observing about a 2 by 2 arc minute piece of 47 tuck with all 10 modules. I'll mention that there's some geo data in the archive that sometimes flip the modules, and so you observe the same piece of sky with a 180-degree flip. That's not optimal for doing this kind of calibration because there's many months separation between them, and so there may be temporal variations. You're better off to do this kind of pointed observation at the same time for all modules. So this will be one of our Cycle 5 programs, and we'll get a good cross-calibration for that. Absolute flux scale, this is a different component of our calibrations. This is a multi-instrument, multi-cycle strategy. So just briefly, this typically targets A dwarf, hot stars, and solar analogs to tie all our flux calibrations on the instruments to an absolute physical standard. Again, typically good to about 1 or 2%. This shows you some of the modes. I won't go into this in detail, but basically the message here, all the scales on the right-hand plot here show you for different subarrays and also different detectors and some are short and some are long. Overall, we're good in terms of absolute flux to better than 2%. And in fact, many of the filters are better than 1%. So our current cycle is aimed at sort of beating down those that are still at 2% to try and get them all to 1% level or less. Stability is another aspect of our flux calibration. These we typically report to project again on a monthly basis. And again, the bottom line here is our detectors are very stable. So you see here covering all the cycles, basically since the end of commissioning. Basic amplitudes are less than 1% or 2% for trending for most of the detectors, most of the modules, most of the filters. There's a slight decrease of maybe 0.1 to 0.8% in the long wavelengths, and so we calibrate that. Decrease in short wavelengths is less than 0.5% per year. And again, since we calibrate this, we can apply these these very long-term trends, so that ultimately your data will have these calibrations applied and taken out. Coronography, similar message actually. The scatter for coronography and absolute flux calibration is good to within basically 1%, worst case being 1.5%. And also for the GRISM, the flux calibration here at the moment is about 3%. GRISM is more difficult to calibrate. You've got more dispersion. You've got spatially dependent flux and wavelength dependence across the detectors. But overall, our absolute flux scale for GRISMs is about 3% or better. The weak lens is another component. I'll just mention that here briefly. That's used for time series observing. And so our flux scale for weak lens is also typically about 1% for most combinations. One of them has about 4%, which we're busy improving with our cycle 4 and 5 calibration, but most of the rest are 1% or less. So the next category of our calibration is distortion, both for astrometry, both relative and absolute. Absolute, the bottom line here basically is we have calibration programs that cover all the primary broadband filters and most of the primary medium band filters. And so our accuracy here, relative position between detectors, is less than 0.01 arc seconds and orientations less than 1 milliarc second. And this graph on the right just shows you an example for target ACK, which also applies for just general astrometry. Before we applied the calibration in the first few cycles, there were offsets maybe up to about 0.1 arc seconds between the modules. Since applying these last year, we've now gotten these offsets down to less than 0.01 arc seconds. And so this applies both for general astrometry and also for coronography target acquisition. The coronography target and also just coronography dispersion, distortion in general has been improved a lot as well. So our residuals for carbonography are about 6 milliarc seconds across the entire image for long wavelength, about 3 milliarc seconds in Y. And for the short wavelength, the residuals are also a few milliarc seconds. So this is crucial for carbonography, where you want to move the star as accurately as you can behind the masks to get suppression. Just a couple of plots here showing our DSF characterization and target act verification. Again, centroiding now is down to a good to a few milliarc seconds. There's also a mode in carbonography for dual channels. So this shows you just briefly an example of what we call this dual channel. So basically, you use a long wavelength mask, but coupled with a short wavelength filter and a detector. And this shows you an example of how this dual channel mode works. So this has been effectively commissioned. It's available for use by the community. And coupled with that is our inner working angle and contrast optimization for dual channel carbonography. So this is initial results involve testing a range of setups for inner working angle on the same star system to basically to ensure that the community has optimal use of this dual channel and inner working angle capability. Turning now to spectroscopy, it's another primary mode of NIRCam, second only to imaging and carbonography, really. So for spectroscopy, the workhorse mode really has been in long wavelength, where you can get wide field slitless spectroscopy across the entire detector in long wavelength. A critical part of the calibration is to be able to calibrate our long wavelength spectral traces, both in wavelength and position, across the entire detector on the long wavelength. And so to do this properly, it involves getting many, many different spectral traces across the detector. So we've been basically building this up, starting more or less in cycles 2 and 3, and now extending into cycles 4 and 5. This plot here just shows you that the bottom line here with red shows you basically the current set of spectral traces across the detector that we will have with cycle 5. These plots show you some of the accuracy in terms of wavelength differences. So we're now at the point where our wavelength calibrations are accurate to about 1.7 angstroms RMS, down from 2 angstroms before. The trace calibration, the sigma, the 1 sigma RMS dispersion is about 0.1 pixel down from 0.2. Again, this is, in fact, this is published. I'll show you at the end the list of references. This is a Pershka video published recently in AJ. Wavelength residuals, again, this shows you the histogram showing what these residuals look like in terms of 1 to 2 arc seconds, 1 to 2 angstroms residual. And this shows you now the map. And so the idea is to get these dispersions flat across the entire detector. So we're well on the way to achieving that with our cycle 5 calibrations. Another aspect of the long wavelength prism is the spectral backgrounds. These impact our spectral extractions. And so the idea here is to observe, to do external background observations. And so the way to approach this is to say, well, which filters have both the largest variation and the least amount of existing data to do the background calibration. Of all these filters, the right-hand plot shows you an example of what the quality looks like once you remove the background. So it is determined that the F277W had the largest variation, which you can see there on the right, and also the least amount of data. And so this would benefit the most from external observations. The other GRISM filters have enough data in the archive at the moment for us to be able to construct background maps based on the archival data. So once we complete the 277, we may then increase observations for some of the other filters as needed. Now, a new mode that we've just commissioned, or that we're in the process of commissioning with NIRCam, is using the dispersed Hartmann sensor. You'll recall at the beginning I mentioned some of the pupil wheels and the filter wheels. Well, the DHS is in the pupil wheel, and it's actually an optical element used more for alignment of the entire optical assembly. But you can also use it for science. So it has basically a dispersing element on it. And so the DHS on the short wavelength provides us the ability to basically provide a dispersal spectroscopy on NIRCam short wavelength. And so this mode has been enabled as of cycle 4 And we're right now in the process of completing some of the calibration programs. In my table at the beginning, you'll see the PID numbers for the calibration programs to enable this. So basically there are two components. There's calibration, which is sort of equivalent to the commissioning of this mode. And then there's characterization to actually see how it behaves. And just to give you a sense of the program 9215, that's effectively the calibration mode for this mode. I'm doing both flux and spectral calibration. And then program 9243 characterizes it basically by looking at a science target. In this case, WASP-18b, one of these hot Jupiters. And the idea is to measure the precision to which you can track the light curves on this target with the short wavelength dispersing element. So there's an example of what we would expect on the transit depth based on the error for this, the expected uncertainties based on this mode. So stay tuned. These programs will be executing during this cycle sometime in the next few months. And once they've executed, then we can declare this mode ready for use. I think there are a couple of geo programs interested in using this mode. This shows you just graphically what the subarrays look like for extracting spectra. So it's basically using what we call a multi-stripe or a sub-stripe mode on the detectors. Think of it as a single object spectroscopy, equivalent to what NIRCam actually offers. NIRCam has a single object spectroscopy mode. This is kind of comparable to that, but different. So stay tuned. You can couple this with long wavelength spectroscopy of exoplanets, and we expect this to be quite an exciting new mode. So I'll finish up. This is our summary of current accuracies for NIRCam. Basically, this summarizes all the different modes that I went through. I'll just speak to these numbers briefly. Our flats basically are 1% total accuracy now for most filters. The wisp noise has been reduced by 40%. The backgrounds agree with actual models to 5 or 10% across our wavelength range. For our abs-flux imaging and also our weak lensing, absolute photometry is better than 2% for most filters, which was used to be 3 or 4% in the first cycle to after commissioning, and many of them actually below 1%. So most of our absolute flux calibration, you can rely on absolute photometry to better than 1%, but we're continuing to improve that. Coronography is also better than 1%, down from 1.5. There's a couple of modes in both long and short wavelength where we need more targets. GRISM, absolute flux photometry is better than 3%. Flux stability is better than 0.5% reduction per year, which we can measure and calibrate and correct for in the pipeline. On the right-hand side, our subarray flux transfer, so mapping from subarrays where we actually do the flux calc to the full array, that's accurate to about 1% or less. One or two filters are at 3%, but we're beating them down. Most of the others are better than 1%. Our stellar L flats are 1 to 2%, and so we're correcting for those. GRISM wavelength calibration traces, they're down. The actual placement is better than 0.1 pixels, and the spectral calibration is down from 2 angstroms. We had about 1.7 at the moment. Coronography target ACK is better than 15 milliarc seconds, and our distortions are better than 0.01 arc seconds for relative positions. The models are much better within an SCA, well below a milliarc second RMS across the entire detector. And also the orientations are better than 1 milliarc second in terms of degrees orientation. And finally, our coronography are down to 2 to 3 milliarc seconds, down from 5 to 10 on the short wavelength and 3 to 6 on long wavelength. So here's where you can go to for documentation. No need for you to copy these down. These presentations will be made available post-facto. But we've got an overview, sort of a high-level instrument page within the calibration status page overall, and also for all the different modes. We've also got a page where we present all of our technical reports, and I've just called out here links to some of the public reports that I've mentioned in this particular presentation. And that's it. I've got some backup material in case we have questions, but I think at this point I'll thank you for your attention and go to questions. Thank you very much.